Hello and welcome to our Day 5 notes of our statistics unit for Algebra 2. Today we're going to explore the concepts of margin of error and the middle 95% interval. So first let's start off with something that we all know a little bit of something about. What is the theoretical probability of getting heads when flipping a coin? Well, knowing that there's either heads or tails, you would say 0.5. That is our theoretical probability. In actuality, do you think that that's always going to happen though? If you flip a coin 10 times, are you always going to get 5? Of course not. It would be reasonable to expect you to get 4 heads or 6 heads, maybe even 8. That would probably be pretty unlikely, right? 8 out of 10, that's a pretty high probability of getting heads. So below is a simulation of flipping a coin 10 times per trial, 100 trials. So every one of these dots is representing the proportion of getting heads out of 10 coin flips. So as you look at the simulation, you'll notice that we have this super small one that's at 0.1. So that meant 1 out of 10 times you flipped the coin, you got heads. It happened. It was super rare to happen because it only happened once on our simulation. So that's our smallest proportion of heads that came up. Now our highest is 0.9, meaning 9 out of 10 times you flipped the coin, you got heads. Now, would you have expected these possible results before we started our simulation? No, probably not, right? Getting 1 out of 10 or 9 out of 10 is a pretty rare event given we know the theoretical probability is 0.5, which is why that's the middle of our distribution here. These are called extreme dots on either end of our distribution, and they are not expected. They are unusual results that happen rarely, okay? It's not that they can't happen, it's just that they happen so rarely. So what I'm going to do is disregard a total of 5% of our most extreme dots taken from either end of the distribution. Now, since we have 100 dots, throwing out 5% of that would mean we're going to throw out 5 dots. Okay? Now, it's impossible for me to throw out 2.5 dots per side, so what I'm going to do is just throw out 2 dots on this side and 3 dots on this side. Technically, I could do the reverse. I could do 3 and 2. I just chose to do 2 and 3. It's just to help us get an estimate. Now, by me throwing out that data, that's leaving me with, well, 100 minus 5, so our middle 95% of our data. So from here to here is considered our middle 95%. Now, what this does is it helps me come up with a way to estimate what's going to happen the next time I flip a coin. So by throwing out those extreme dots, you'll see that my new smallest is between 0.2 or 2%. And my other one, oops, I said 2%, I meant 20, 20%. And then at my high end is 0.8 or 80%. So if you want to think in terms of decimals, that's 0.2 and 0.8 on my distribution. So if I were to take one more sample of n equals 10 coin flips, I can reasonably expect that the next set of proportion of heads would be somewhere between 0.2 and 0.8. Okay? Notice how I disregarded the 0.1 and the 0.9. Because we know that these estimates will vary from sample to sample, it doesn't make good sense for us to give a single estimate as what we think the true proportion for all coin flips of sample size 10 are. So instead, that's where this middle 95 confidence interval that we just came up with is helpful for us. Now we can figure out this 95% confidence interval by adding and subtracting something called a margin of error to our estimate. The interval is computed using the margin of error because we know that each sample is going to give slightly different estimates. And in other words, our margin of error is our wiggle room to account for that sampling variability, meaning every time I flipped the coin 10 times, I got something different. So basically what this is saying here is that when I have the center of my distribution, going this way is a margin of error, going this way is a margin of error, which is capturing my middle 95%. Now, where have we talked about middle 95% before? Back in Unit 13, actually, when we looked at our normal distribution curve. We have seen this bell shape where the middle of our distribution is our mean. So that's similar to what you guys are seeing in this sampling distribution. The mean's at the middle. And then I have 2 standard deviations marked off in either direction. Now, if you guys recall, between the first 2 standard deviations is where we captured 68% of our data. But as you may recall, it was within 2 standard deviations on this standard normal distribution that we captured 95% of our data. So what is the area under the curve between -2 and 2? It was 0.95, so as a whole percent, 95%. Okay. Now again, this picture you guys are looking at is called a standard normal distribution because the mean is 0 and the standard deviation is 1. Now, I have labeled for you your margin of error, which is that wiggle room I was talking about that helped us capture our middle 95. I look to the left and I look to the right here. It's my wiggle room about my mean that captures the middle 95 of what would be a reasonable estimate of what's next to happen. Based on the way I have this labeled, you can see that 2 standard deviations is equivalent to what I have labeled as the margin of error. And that's a really important formula to understand. So let's put it into practice. Given a normally distributed population of IQ scores with a mean of 100 and a standard deviation of 15, between what 2 scores would you expect to find the middle 95% of all scores? Okay, so first of all, let's just even draw a bell curve like what we did back in Unit 13. Okay, so here's your middle with your mean at 100, and I'll mark off 2 in either direction. Now I'm going to add 15 to mark off each of my standard deviations. So this is 115 and 130. Okay, and then I'll go in the other direction too. So this would be 85 and 70. So to answer the first question, between what 2 scores would you expect to find the middle 95% of all scores? I actually know it's going to be these 2. Because that's going to capture that middle 95%, which is 2 standard deviations on either side of the mean. Now, kind of walking through these questions here where it says, what is the margin of error? Well, margin of error is just 2 times the standard deviation, which they told me was 15. So if you go 30 in either direction, which is our margin of error, or 2 standard deviations of 15, that's where you're going between 70 and 130. That's my middle 95. Now, this means that we can reasonably expect the true mean of all IQs to be in that interval. Now, when you guys are looking at middle 95% intervals, there's always a low reasonable expectation and a high reasonable expectation. As you guys just saw in the previous example, it is reasonable to expect that the true average of all IQ scores is somewhere between a 70 and 130 based on our sampling. So your low estimate's a 70 and your high estimate is a 130. If margin of error is equal to 2 times the standard deviation, it's also true that margin of error is going to be equal to the highest reasonable minus the lowest divided by 2. So I'll kind of simplify this here in the margin. High minus low divided by 2. So Kathy was surveying the students about average studying time for AP exams and found the interval for plausible mean for a given sample size of 40 students to be 5.3 to 16.5. She then increased her sample size to 160 and the interval changed to 8.4 to 12.2. Calculate and compare the margin of error for both. So for our sample size of 40 students, again, they were saying between 5.3 and 16.5 hours. That's what captured her middle 95% of her sample there. Margin of error is high minus low divided by 2, which is going to end up being 5.6. Now she'll do the same thing for 160. Now again, that interval was 8.4 to 12.2. So high minus low. Oops, let me rewrite this again. High minus low divided by 2. And you get a 2.2 when you do that. So, what do we notice here? Well, we went from n equals 40 to n equals 60. So what you're seeing is your sample size increased. What happened to our margin of error? Decreased. Now, this shouldn't be shocking based on simulations we've done in the past. As sample size increases, our standard deviation and mean and our sampling variability, I said mean, I meant margin of error and sampling variability would also decrease, meaning your data is getting tighter together. So filling in your blanks here, as sample size increases, our margin of error decreases, which ultimately means our standard deviation also decreases. Because margin of error is 2 times the standard deviation. Okay, example 3. Given a normally distributed population of SAT math scores, we can reasonably expect that the 95% of scores would be between a 510 and a 590. All right, so here's your bell curve. Here's your center right here. Okay, now based on what they're telling me, my low end here would be a 510. My high end is a 590. So if I want to figure out my margin of error, I'm going to do high minus low divided by 2. So what is that? 80 divided by 2, which is 40. So what that means is if I were to kind of work my way on this curve here and add 40, this would be 550, which makes sense then because another 540 would give me 590. Margin of error is always equal to 2 times the standard deviation. So if we know our margin of error is 40, then it stands to reason that our standard deviation is 20. So kind of filling in the rest of our gaps here, and I add 20 to kind of fill this in, this would be a 570, which again makes sense to continue my distribution, and likewise going backwards, this would be a 530, which back another 20 would make sense to get a 510. So I've completed my distribution curve. Again, your mean is right in the middle there. What is my mean? 550. All right, let's get into some harder context problems here. Now, in life, we're not going to do a ton of samples. We're going to do one sample and then use that one sample to help us make estimates about what is likely to happen based on our middle 95% interval. So let's say Williamsville Central School District is planning a district-wide trip to Marineland, Ontario. A random sample of 36 juniors revealed that 12 of them planned on attending the district-wide junior trip. Okay. Now, right there, I'm going to write down my p-hat. That's my sample proportion. We revealed that 12 out of 36 of them that we sampled are going to go, which that's 1/3 or 0.3 repeating for reference. In order to best estimate the true proportion of all juniors attending the trip, we run a simulation based on a sample size of 36, assuming the probability of the juniors attending is 0.333. So we're running it based on our sample, running that simulation in the computer. We run this 250 times. So what that means is in your distribution here, you're going to see 250 dots, okay? And every one single of these dots is representing the proportion of juniors that are planning to go. So that's our proportion of successes. All right, so what is the population in the sample, or in the scenario? Well, the population is who we're trying to get information about. You're trying to get information about all juniors in the Williamsville Central School District. Now, what is so I'm going to label this with P. What is the sample? Well, the sample was the 36 juniors you got. Sometimes I think it's easier to identify the sample than the population just because the sample is who you pull out. It's the small numeric number. I guess not always necessarily small, but it's not going to be huge. It's the sample that you're taking to get information about to then make inferences about the larger population. Okay? Now, this is considered categorical data because this is a yes or no question. You're either going or you're not. So this is a proportion. As soon as we start talking about proportions, that's categorical. If we were talking about like averages, that would be like X bars, that would be quantitative. Okay, so success versus failure, that's our categorical data. Using the results from the simulation, calculate the middle 95% that we expect to contain the true proportion of all juniors in the district to expect to go, and round to the nearest hundredth. Now, when it says using the results of the simulation, this is where you guys are going to look right up here. Now, your middle 95% is computed by doing the mean plus or minus 2 times the standard deviation, which is given to you. Now, that standard deviation is the same thing, or 2 times the standard deviation is the same thing as the margin of error. That's our wiggle room. That's going to go in either direction of our center to make a best estimate of what's going to happen. Okay? So if I go ahead and type in 0.335 plus or minus 2 times 0.087, okay, you would end up getting 0.161.509. But make sure you round. Okay, that usually gets people. So 0.16.51. Okay, so what does this mean? It means it's reasonable to expect, let's talk in percentages because sometimes that's nice, just in words. It's reasonable to expect between 16% and 51% of all juniors, our population, will be going on the trip. Okay, so something I want to point out here is notice how I tied it back to the population. I'm using my middle 95 to make an inference about all juniors in Williamsville Central School District, which again is the population. That's the whole point of doing sampling, to make inferences about a larger population. So based on our findings, would you be comfortable placing a $20 bet that at least 60% of the junior class would go on the Canada trip? Well, why or why not? Well, based on our sampling, at most, I'm probably comfortable with 51%, but 60% is outside of that interval. It certainly could happen, but it's highly unlikely to happen based on my sampling. So I'm going to say no. 60% is outside the middle 95%, and therefore unlikely to happen. All right, and that concludes that example. Let's try one more. A random sample of 78 bags of potato chips at the Frito-Lay factory in Dallas, Texas was analyzed and found to have a sample mean weight of 9.1 ounces. We ran a simulation and found that the mean of the sampling distribution to be 9.09 ounces with a standard deviation of 0.005 ounces. So I'm actually going to start with what's the sample, because I think that's easier. The sample is those 78 bags, right? Let's say 78 bags of potato chips. Oops, potato. At Frito-Lay in Dallas, Texas. And yes, I looked that up. I actually have an uncle that used to work there. So I had to confirm it. I was like, pretty sure it's in Dallas. It is. okay, so those 78 bags, they are helping us make an inference about all of the bags at the Frito-Lay factory. Now, is this quantitative or categorical? Well, categorical would be talking about a proportion, like a success versus a failure. This is me just measuring the weights of the 78 bags, adding them all up and dividing by 78. So this is quantitative data because we're just looking at the average weights. Using the results from the simulation, find a plausible interval containing the middle 95. So again, we're going to take our mean, which is 9.09, and we're going to add or subtract 2 times the standard deviation. So what this means is it's reasonable to expect the average weight of a potato chip bag at the Frito-Lay company is somewhere between a 9.08 and a 9.1. Based on the results above, do you think any customers should complain that they are not getting a full bag of potato chips if the chips are labeled as containing 9 ounces? So taking out the fact that people love to complain, if the bags are advertising 9 ounces and they're getting on average between 9.08 and 9.1 based on our statistical analysis, should they complain? Absolutely not, because on average it's reasonable to expect that they're getting actually more than 9 ounces. All right, so in summary here, everybody, what we're doing is we are looking at the middle 95% of our data, and we're calling this what's usual, expected, reasonable, something that's to happen. So when I did my sampling of the Frito-Lay company and I came up with my middle 95%, like I said, it would be expected that the true average of every single potato chip bag in that factory is between 9.08 and 9.1. Okay, if I were to actually do that, but I'm not. I'm just doing a sample and then I'm running a simulation based on that. Okay, so this helps me make inferences about the population. Now, it would be unusual for it to be higher than that. That's anything that falls outside of our middle 95%. So that would be a higher weight than 9.1 or a lower weight than 9.08. Okay, so again, anything that's inside the middle 95% is what's expected, expected, usual, reasonable, something that's likely to happen. The outsides here, it's not that they can't happen, it's just that they're super rare to happen, and it would be shocking if they did happen. So those are your unusual, unexpected results. Okay. Additionally, one last thing we talked about today is that your margin of error is that wiggle room that's on either side of the mean that captures your middle 95, and your margin of error is equivalent to 2 standard deviations. Okay, so having this diagram memorized and knowing those relationships is very beneficial in this statistics unit. And that concludes our Day 5 notes.